Hello, I'm Mr. Sean, and I'd like to run you through your higher and standard level course review for IB Chemistry this year. So we have this presentation here. It's shared with you in Google Classroom. And if you go to the next slide, you'll see this is your assignment. You're going to be individually assigned a subtopic, for example, 1.1, B2, etc. They're going to be assigned this week, and you will prepare a video showing that you can demonstrate mastery of the applications and skills for that subtopic. You'll have to look up the criteria in the IB Chem guide, which is linked here. All right, and note that mastery of the applications will be necessary, involving covering the understandings. Keep presentations timely, less redundant, and integrated. These should be naturally worked into your presentation, not treated as separate statements. So don't just go down a list and tell us what you know, okay? So each subtopic is going to be presented in a context that'll be assigned, and we'll look at those in a second. This is going to require you to apply your understandings, not simply repeat them from a presentation or textbook, though these types of things are certainly useful. All right, presentations are going to be 5 to 7 minutes long. You're required to pre-record your presentation for others to review with. You will present your video in our live meetings. You will pause your video 3 to 4 times and ask questions and solicit responses from your classmates, kind of like you would do with an Edpuzzle video or live instruction lecture type thing. All right, the live session will be recorded as well, and everything will be uploaded for posterity. All right, topic 1.1 is what I'm going to go through with you right now. Okay, so let's look at the next slide. What you're going to do is you're going to make a copy of this slide here and just change the information. The topic 1.1 is Introduction to the Particulate Nature of Matter and Chemical Change. There are 3 applications and skills: deduction of chemical equations when reactants and products are specified, application of the state symbols S, L, G, and AQ in equations, and explanation of observable changes in physical properties and temperature during changes of state. So our context here that we've chosen is to look at some precipitation reactions. Okay. Real quick, before we actually jump into that, this is the list of all of these subtopics. Okay, they're all listed out here. They are indicated whether they're core, so SL and HL, or if they are the additional higher level material, which is just HL. We will have you guys sign up for or assign these, and each of you will take one to record your video. We will present them in class, and then we will do the next batch. Okay, so we'll probably do this 2 or 3 times. Have no fear, SL, you guys won't be expected to do any of the HL only or AHL topics. Okay, so you can see topic 1.1 here for us, precipitate reactions, and we have put this one together to kind of demonstrate an example of what we expect. All right, so in this link here I have a little video. So in order to show my understanding, I need to be able to deduce chemical equations when reactants and products are specified, apply state symbols, and explain the changes in physical properties that I observe and temperature during these state changes. So let's take a look at some precipitation reactions to see how this works. So here we see 3 different solutions. They are, from left to right, copper 2, iron 3, and iron 2. Notice they're all transparent, and they display their characteristic colors for their aqueous forms. So what does aqueous mean? That's right, aqueous means they're dissolved in water. So these are the aqueous forms of these ions. When sodium hydroxide is added to these solutions, we can see the formation of some precipitates. Iron 2 hydroxide is an olive green solid you can see near the surface in the right beaker, in the right test tube. When sodium hydroxide is added to iron 3, the precipitate is a blood red brown color seen here. Okay, again, it kind of floats and suspends in the middle. It will eventually settle. Finally, when sodium hydroxide is added to copper 2, we get copper 2 hydroxide, and it's a dark blue solid. So these solids are insoluble in water. What does that mean? What does it mean to be insoluble in water? Right, they don't dissolve. Okay, simple as that. So, when these precipitates and solutions are allowed to stand for a few more minutes, the more reactions take place. The copper 2 hydroxide decomposes into a black copper 2 oxide. Can you predict the other product of this decomposition? I bet you could if we looked at an equation. So we have copper 2 hydroxide. So copper 2 is Cu2 plus, hydroxide is OH minus. So when I combine these two, I get copper hydroxide, and this is a solid. Let me get that in focus for you. Okay, copper 2 hydroxide, solid. S for the solid state. Okay, this decomposes into copper 2 oxide, CuO. Okay, copper again, copper 2, Cu2 plus, O2 minus. Put those together, we get copper oxide. This is also a solid. What is our other product? Correct. The other product is water, H2O, and water at room temperature and pressure is a liquid. All right. Notice we do not see any bubbles when this happens, which would indicate any gas forming like H2 or O2 or H2O gas, the steam. Okay, so we know that water is a liquid here. The iron 2 hydroxide precipitate, when allowed to stand, oxidizes or loses an electron to form the iron 3 hydroxide, which is a more stable under these conditions. So hence we see the color change from the dirty green, olive green precipitate to eventually we start seeing this red-brown, dark red-brown color showing, which is our iron 3 hydroxide. When it does this, it reacts with oxygen from the air, okay, in this reaction here. We have our iron 2 hydroxide. So iron 2 is Fe2 plus. Again, hydroxide is OH minus. Combining those, we get FeOH2, and that is a solid. It is going to react with oxygen from the air, so O2 gas, G for gas, and some of the water from the solution, H2O liquid, and that's going to form our iron 3, Fe3 plus, and OH minus, iron 3 hydroxide. Again, a solid. So let's look at the equation for the formation of copper 2 hydroxide from the reaction between copper 2 nitrate and sodium hydroxide. So our reactants are copper 2 nitrate, so we have our Cu2 plus, and nitrate, NO3 minus. This was the clear, transparent solution, the blue solution before. So this is aqueous, Cu, NO3, 2, AQ. Okay, this is reacting with sodium hydroxide. Sodium hydroxide, sodium is a Na plus, hydroxide, OH minus. So we have a 1-to-1 here. NaOH, also an aqueous solution. This is going to form our copper 2 hydroxide in a double replacement reaction. So the two cations will switch places, or you can think of this as the cation from one reactant combines with the anion from the second reactant and vice versa. Or we can think of it as the two outside ions and the two inside ions are getting together. So however you want to think of it, it's a double replacement, and we have copper and hydroxide, so copper 2 hydroxide, CuOH2. That is our solid. In a double replacement reaction, one of the products, at least, needs to be a solid, a liquid, or a gas, not a solution. Okay? Our final product then is what? Good. Sodium nitrate, NaNO3, and this is completely soluble, so AQ. All right. Next step is to balance here. We always need to balance our equations. The ones up above here are already balanced. This one is not. So we can balance this by inspection simply by looking at the elements that we have on one side of the arrow and making sure they match the number and type of elements we have on the other side of the arrow. So 1 copper, 2 nitrates, only 1 nitrate. So we can fix that by adding a 2 here in sodium nitrate. Now I have 1 sodium and 2 sodiums. We can fix that by adding a 2 in front of sodium hydroxide. All right, now we have 2 hydroxides and 2 hydroxides. Just check real quick, 1 copper, 2 nitrate, 2 sodium, 2 hydroxide, 2 hydroxide. We are balanced. The last thing we want to look at here is sometimes the molecular form of the equation is not the best form. Sometimes we want to show what's called a net ionic equation, showing only the ions that are actually taking part in the reaction and eliminating spectators. Okay, spectators are ions that do not take part in this reaction. They're literally just watching. They're not doing anything. So what we do is we split all of our aqueous species into their ions. Okay, we leave solids, liquids, and gases alone. So I'm just going to rewrite this in what's called the complete ionic equation. So I have copper 2 plus, I have 2 nitrates, NO3 minus, I have 2 sodiums, and 2 hydroxide. Okay, copper 2 hydroxide is a solid, we're going to leave it alone. And I have 2 sodiums and 2 nitrates. Okay, notice I didn't write my states here on the ions. We can assume ions are always aqueous. In this middle step here, when I write my final equation, I will want to indicate that those are aqueous. Okay, so we can cancel out ions that are on both sides of the equation unchanged. All right. These are our spectator ions. So sodium, 2 sodiums, 2 sodiums, they're not doing anything. They came with the hydroxide and sodium hydroxide, but they're not really doing anything. They prefer to be dissolved, which means they're in their ionic state. The same goes for nitrates, 2 nitrates, 2 nitrates. Nitrates came with our copper 2 ions in our copper 2 nitrate solution, but they are not going to combine with sodium to form a solid because they prefer to be in this aqueous state. So they're just NO3 minus ions. We're going to eliminate those from the equation. All right, there are no other spectators here, so I can rewrite my final equation. Cu2 plus aqueous, there's our copper 2, plus 2 hydroxides, OH minus, and that is yielding our CuOH2, our copper 2 hydroxide precipitate, our solid. Okay, thank you very much for paying attention, and I look forward to your presentations.